Today we cover how to make a hole. And if I were you, I would be thinking, how much is there possibly to know about making a hole? And we're gonna find out. The answer to that question starts with, there are at least 3 drawers full of information about making holes. Here's one of them. This one is partially involved in making holes. We have here Forstner bits, and we'll go around through some of that. This drawer is also for making holes, some of them with special shapes and some very small holes with carbide bits and special materials. And then of course we have our everyday holes with regular drill bits and conical types of bits and tools for making adjustments to holes. So this morning I thought, am I really about to make a video, maybe an hour long, about how to make a hole? And does anybody really need that? And one thing is, there are millions of materials and millions of needs that start with making a hole. The other thing is, my overall goal for all of this content is to show people how to design and build robots. I have loads of colleagues at the PhD level in the robotics space. I'm not a professor, but if you were a professor, you're having to learn, in order to teach robotics, mechanical engineering, electrical engineering, software engineering, networking, and so on and so forth, in order to even begin as a robotics expert. Okay, and so this is a lot, and to be honest, the folks I see that are earning their PhDs in robotics related fields, they're building prototypes and they may not know most of this content. And so this video is dedicated to those experts, and you can watch this video and not tell anybody that you had to go all the way back to square one and learn to make a hole. Okay, how do we organize a video like this? I have no idea, but we'll start with a goal, that is for the viewers to come away with a toolkit of strategies related to holes, instead of trying to cover every material possible, thicknesses, and every type of tool, like physical tool. I'm going to start with a series of tips. I'll try to make those 60 seconds top and just kind of blast some neat information, and then I'll go from there and try to break down sections afterwards. This is a hole guide. It's indispensable for reasons I didn't realize before I owned one. One of them is that perpendicularity is much harder to achieve by eyeballing, and you'll notice that if you ever try to make dowels aligned, it looks atrocious if you don't have something to guide you, and this is an example. It forces you to narrow down the range of sizes that you're using, which causes your designs to become simpler and also more commonized with the available hardware that's out on the shelves and the other tools that are going to be involved in dealing with your holes. The drill guide also teaches you to look more closely at details, such as learning that regular drill bits do not perform cutting on the sides, which preserves this steel on steel action from damage. When you lift this up, you get to discover how much material was removed and collected under this little gap from your hole. And just when you think that it has limited the depth of your cut that is possible with your drill bit, you realize that the hole you have made with just a little bit of depth is appropriate to allow that hole to be the guide itself for the rest of the depth. A automatic center punch like this one is indispensable for performing accurate centering of a hole that you need to locate before you drill it. It prevents the drill from walking, which is an action like this, where the drill will move away from your desired location. And if you use it a lot, which I do, you will find it is crucial for metal work, where lines must be more precise. Might invest in a highly reputable brand so that you can do things very cool, like even adjust the force that's behind your center punch. Taking control of the force can be crucial because you can simply split a material if it is too weak for the amount of force you're giving, and you can always measure that force and check it how much just before it clicks to assign a rating for yourself and decide what your cheaper device is to be used for. When you need precision and control of the depth of a drill, you're going to have options like purchasing a set of these collars, which come in packs for different sizes, and then they have a set screw to set the depth. So instead of measuring, you can just be sure beforehand how deep your hole will go. This is good for dowels, etc. An alternative is to make that drill stop out of anything that you want, such as this HDPE, or I've also found that when you have control of the force that you're applying, you can simply get away with an O-ring or twin O-rings to prevent them from rolling up and down. Evaluating the depth of a hole can be difficult, and your calipers usually have a feature on the bottom which allow you to slide that thing in and then slide down your measurement and check the depth, which gives you the depth of a hole as long as you are aligned such that this touches the bottom. With funny shapes, it can be difficult to measure with this feature, such as if I want to go to the bottom of that thing, and in those cases you can usually buy an attachment that has a very precision bracket to cause you to be certain you have parallelism with the flush edge and a direct perpendicular depth measurement. If you need a hole that is concentric with a round thing, then finding the center can be non-trivial. Online you'll find loads of ways to do this, but depending on the accuracy, here's one way. If you have a square with a 45-degree angle, you can build your own bracket that you can keep forever. It just needs to have an edge that is perpendicular to this, and in my case, I met the joints at the top edge of my ruler, so now I can place that there. I can V up this round thing. Boy, sorry about that. Here's a better job. The advantage of this method is if you're just trying to eyeball the diameter of a circle, it's very easy to miss the center point, and you can either be off in some angle and you'll get 97% of the full reading of the diameter, or you could be offset and parallel, and this one would get you 95. So very small values to notice and very major offsets from the middle. And so that's where this square forces the shape to be aligned. And we always screw through the center with that V shape. We can measure the diameter at the same time by noting from this point to that bottom edge on my ruler. To make a hole in any thin material, it is advised to use the center punch and to reinforce the region behind your hole, or else this can move around. It is also advised to clamp the two so that this does not spin around and cut you when the drill bit grabs. The more support, the better the result, and safer. This is called a step drill bit. It's my favorite drill bit, I think, and it is super clean to go through any thin material. This is just going to plow through as soon as I've done the starting, and yes, you can start a hole with this. It has a nice tip for such. This stepless variant is another version of the same type of tool where you have more control over the exact size of the hole, and you can mark it as desired with a Sharpie on the face that doesn't rub. Also, these, even the cheaper ones, this is a Harbor Freight one with a softer material, they last quite a long time as long as you're not trying to do heavy steel. If you need a hole in an irregular surface like this curved surface, that's when the Forstner bits come in handy. And the key features for this to pay attention to is a very rigid shaft and a beefy material here that will take out the entire, it will cut shavings out of the entire hole region. This is a time when the force of that uneven contact will cause the flex of an ordinary drill bit, and it would also disturb the cutting when you have the entry beginning on something like a spade drill. This is probably the fastest way to put a large hole through wood, and this is probably the slowest way. And you don't need a drill press, but this is what is recommended if you need the perfect vertical alignment. The Forstner bit is special because it doesn't care about what region it's cutting, and it will put a nice flat surface there, as well as a datum point / pilot hole for your next hole if you want to have a different diameter driving through. The Forstner bits don't give you any guarantees about the cylindricity of a hole, which means it could actually turn and travel a different direction if you don't hold the drill steady. Imagine the red lines are the material you're cutting and the blue is the bit. You have a moment, which is the only thing to keep your drill aligned, that is caused by the contact point back here and up there. That moment is small because the distance across is small. And on an ordinary drill, you have these contact points all the way back at the start of your hole and all the way forward. And so this has a strong moment that keeps itself aligned. This is disregarding the rigidity of the metal of either one of these. I keep on saying ordinary drill, but I really mean twist drill. This is a twist drill bit, both of these are, and why would you choose one over the other? This one has a hex shank, and that's best for easily swapping in and out of your modern tools, which have this type of chuck. You might choose the round shank twist drill for precision. That is because they fit inside of these chucks, which have a higher precision than the clip-on chucks. Okay, so we have better runout, less runout on this compared with this. There's wobble that you can see, and that comes from two things. One is the looseness inside of that chuck. The other difference is the manufacturing of these things, where this is best case, medium case, worst case for the manufacturing accuracy. If you see a fillet here, then you're likely looking at something that's been machined from one piece. That means it was fixtured, and they can control that the the alignment of the end and the chuck side is aligned, whereas this has been manufactured by a press fit, and these were two pieces were manufactured separately. They press fit the bit into the holder, and this is far less accurate. If you need to make a hole in a round tube, then I recommend clamping it in between two flat things as I've shown here, and I recommend that the height is as close as possible to even. That will allow you to measure wherever you need to measure along the length, and your pencil will be very close to the surface if you're taking that measurement, and for example, you need to be at the very top edge. It also gives you the opportunity to use your drill guide and make sure that your hole is going to be vertical, and it's going to be tangent with respect to that, it'll be perpendicular to that zone on that face. If you need multiple holes to be along a straight line on the tube, then you can see in this case we have it a little bit crooked. So first you would cut one end to be perfectly flat, and then you can use a square to line it up anywhere you go, as long as you're touching both faces, the edge of the ruler and the edge of this aluminum, then you're going to have a straight line that is vertical along the tube. If you need an accurate hole in a flexible or floppy material, then this can be quite difficult. And the appropriate use cases would be like for making gaskets. This is a good time to use a punch. That's going to give you something that's accurate, and you have plenty of time to adjust because you're not controlling speed at the same time. And a hammer is going to put that hole right in there. You get to retain the circular piece in case you needed the hole, the circle instead of the hole. And you need to make sure that you have some sort of compressible, sort of soft material at the base to work as a sacrificial material, or else you'll damage the edge on this. I would make the same recommendation even if your material is thicker, like foam, and I would press down as far as you can before you punch so that you're only trying to drive it a small distance to the base. And also, you get something that's pretty clean. These punches are steel, and they don't usually come in a whole lot of sizes, and I don't usually need to make a lot of these kinds of holes. So keep in mind that if you have any steel lying around, perhaps even aluminum for softer materials, you can just sharpen the edge of a thin tube and it will work as a crude punch and be pretty effective. If you need a hole that is fairly cylindrical like this that I'm going to try to pass through all three of these boards, then you can start with the hole guide to make sure it's vertical, and then you can move to just a spade bit if you don't have something nicer, where the point will be guided by the hole that you have made. After you use your hole guide, we still only have a little bit of depth made, so absolutely be sure to chase this all the way through the board by removing the hole guide and finishing your hole so that it passes through. Clamp my board on a sacrificial piece of material that is hard so that it prevents the tear out, making an ugly part on the back side of this hole. Okay, and so this reduces how much tear out I get on the edges of this wood and helps make sure that my hole is continuous as I'm drilling. We don't have a changing geometry on the backside and changing forces and pressure. If your hole is going to have two different diameters, such as a countersink, then you need to drill the larger one first. If I were to attempt this hole with a spade bit or a hole saw, I no longer have the security of a material holding my tip. So that would be a little bit dangerous and also come out very messy. At the beginning of your hole, you will have the surface of the wood to give you an indication about whether you're holding the bit straight or not. So if I'm upset, that tells me that I'm leaning to the right. So I can adjust my stance, or I can get a better grip or something to lean my elbow on to hold the drill in a way that is more certain to be vertical. Or if I don't need that precision, I can just proceed and keep my eyes on that surface. All right, now I want a 7mm hole to be an 8mm hole, so I can pass this M8 bolt through it in aluminum. That's the 7mm drill. We're gonna go to here, but since there's hardly any cutting to do at the center of the material, this drill will pull through very aggressively. So we want to maintain control, and so we'll step up one step at a time. If your drill is biting aggressively and pulling your drill into the material, then this torque setting comes into play. This drill setting means we're not going to limit the torque by anything but the motor itself. And these settings are progressively reducing the torque, the max torque that the chuck will turn using a clutch. Usually we're pushing down while we drill, but in this case I'm likely going to be pulling up so that the drill doesn't tear through very rapidly. And I'll go ahead and put it on the drill setting, and then I'll control the speed of the rotation using my finger because I have experience with this, and observe how fast I need to go with my eyes. That was 7.5, now we'll go to 8. Just a second ago I was on the high speed and I switched it to lower speed high torque because I had run out of torque on the motor. It's possible to do a better job than I did, but you'll notice the marks across the inside diameter, and it's going to be a less accurate hole than drilling from scratch if you're drilling a pre-existing hole. Then I'll use this deburring tool that looks like that to put a chamfer and clean up the burr on the edge. I just did that project so I could show you some runout stuff with my favorite magnet. Just a plain old Harbor Freight magnet. These guys can fixture things in place on steel. Okay, this lower bit I had in storage, and this is definitely one of the press fit sets of hex shank twist drills, and this one is machined. So this was more expensive. This is a cheaper, older set that I had put away because I don't like them. The runout is awful, and you can definitely tell they press fit this and then they crimped it inside of that steel hex shape. So I'll show you. We have press fit and machined manufacturing. The cost is cheaper and more money, and the runout is worse or better. So the cool thing about this drill is that you can gain accuracy by setting this in a more accurate drill. That's the upper one that costs a little bit more. Like Milwaukee, if you buy a name brand, they're probably doing these, doing machined bits these days. Okay, this is the nice machined bit inside my drill with the 3-jaw chuck. The runout looks like about 5/1000ths of an inch, and that's more precise than we'll ever get with our hands and our, just a non-machining setup. If you consider 5/1000ths here midway, then down at the tip, you could maybe double it since the length of the lever is doubled. Now we've got the press fit bit. Who wants to take a guess at how much runout we'll get? I'm gonna guess it's double, and this will swing almost 10 or 15 notches. Let's see. Oh, baby. Lastly, if we have a nice ordinary twist drill with no hex shank, we get just a hair less than our first sample. And so that runout is not coming from the tool, the bit, it's coming from my machine. And so now we know if we need accuracy, we can go from the clip-in chuck to the 3-jaw chuck if you have a nice bit that's machined. And if you have a press fit bit, you're not gonna gain any accuracy by moving over to the actual drill instead of the driver. Okay, the last thing to note is that rigidity of the work holding and the tool holding isn't rigid enough to create a huge problem. So the round zone of this cheap bit is still really nice on the runout. We just don't, we can't measure it the way we're holding it. So what you'll get with a worst case tool is it's going to wobble or move around or be a little off center when you begin, and you'll have some entry that's ugly. And then once that material you're cutting is holding the bit itself, then it's going to drive true if you're holding this by hand, etc. So you don't necessarily, you won't see all of that inaccuracy in your work, just near the starting zone and the location. Okay, in construction, this is called a driver and this is called a drill. This may also be called an impact driver. In auto mechanic shop, this is called a driver and this is called a drill. In business, this is called a driver, and his action is called drilling the ball. At school, this is called a drill, and he is the driver. Just describing a little bit why I've crisscrossed terminology, and you can expect that I'll continue to do that. This here is a part, and this whole thing is an assembly. Just a second ago, it was a part, and now it's a workpiece. And I might call this whole thing in my hand a tool, but if you talk to a machinist, then only this is the tool. Oh my gosh, we're safe. And that's the machine. Let's say I need a hole in a slot that's just a little bit wider than the slot width. That's the case in order to build this assembly where my fastener is just slightly wider than my steel slots. If you don't need too much accuracy, you can just do it by hand, and I recommend marking the location, the size that you need to clear. And you can just use the conical bit to chew away at it, and I'm going to be pushing over to the right at the area where my cutting needs to happen. Whoa. So you can see here that it comes out fairly true, but your alignment up and down won't be perfect. And in this case, you can see I didn't reach over to the right as far as I had planned. The most accurate method would be to trace your slot onto the place where you're going to work, onto a sacrificial material, and draw and drill a hole there using your guide so it's vertical. And then you can clamp this full assembly with sacrificial material on the front and back and make it very rigid. And then your drill bit will not care about where the material is or isn't on the steel, and you will put the hole exactly where you want. And you have to make sure that you've clamped it in the alignment at the location that you need. Next, we're going to learn to true up a hole that has a burr on the edge, get us at a clean surface, hopefully a round surface. Here's a close look at the edge, which has a burr that may interfere just a little if I want to add a fitting like that. For this, I recommend a drum-shaped tool that has a 90 degrees here so that we can hold it directly vertical. We're not fixtured vertical, but we have a pretty good chance of getting it right. That was separate from deburring because we still have just a small burr on the inner edge here, and that's suitable for a deburring tool. And to get the angles right on this, it's different for every size of hole, inside or outside, and you need to basically practice this a little to get a feel for where you'll position it and how you'll sweep it across. I'll try to get the top edge here. And some materials that want to bite and gouge, if you can adjust your angle, then you may be successful, or you might find that this pair of material and geometry and this tool are just not suitable. When you're using the drum, I'll recommend that this diameter is somewhere around half the diameter of your hole. If it's very small, then it's easy to cause gouges. Imagine this now from the top surface. It's easy to gouge or be inconsistent about your cleanup work if you're working by hand. And if it's too large, it's very likely that the drum will do a jittering. It'll grab here, and then it'll launch you over there, and then it'll grab here, and it'll launch you over here, and you'll have difficult to control it. So somewhere around half, as large of the diameter as you can get without this, and you'll know once you get started very quickly. Also, I was just working with a thin wall material, but deeper materials. This is also possible, but you have to check and keep track of whether you're staying true and keeping the hole in the same overall geometry that it was. If you use a smaller bit with a small radius, then it's easy to make these gouges out of alignment, whereas the large one, so that only takes a little material to make that gouge, whereas the large one, you'll feel a strong force against the wall if you start going out of alignment, and it's just easier to notice. Let's talk about small holes. So to me, small is in the range of the bottom few options in a kit that comes like this. When you are drilling, most of the cutting is all happening here at this front edge and the exterior of the hole. And so this distance, we can call that a radius, is going to be 4 times larger if your bit is 4 times larger. And so that means the speed of the cutting edge is going 4 times faster. So we care about the speed that this zone is traveling. And for example, these two, the 2-inch one is traveling twice as fast as the 1-inch one for a given fixed RPM. These kits with the hex shank are sold in packets at the hardware store. They often finish just at 1/8 of an inch or 3.2 millimeters. And the range of those sizes is appropriate for the range of this driver. We have maximum of 2,800 RPMs, which is appropriate for the smallest one, I would say. And speeds and feeds are a very interesting science that you could go way deeper, but let's just say, as a rule of thumb, if you don't have a rule of thumb, use that smallest one is going to use the highest speed. And the largest one will use the largest torque to cut the same material at the same approximate rate compared with the smaller ones. So if you go into small holes, these are ranging up to 1 millimeter, 2 to 3 millimeters, then I recommend that you pick up one of these packs so that you can get all of the different sizes you need, increments of 0.1 millimeters, because the precision matters more with a small hole. And they all have a 1/8 inch shank size, or maybe 3 millimeters, but in any case, both of those will fit inside of a typical rotary tool, such as Dremel, right inside of that collet there without any adaptations. When you are working with small bits, especially smaller than 1/8, then these 3 jaw chucks in your everyday drills will lose their ability to hold it tightly and accurately. So this is one of the reasons we start moving over to collet-based tools for higher speed and higher accuracy. If you need a small hole in wood, there's probably something wrong with your design and you should adjust it. If it's a small hole in fiberglass or carbon fiber, or one of these materials that involve ceramics, then it's going to be an abrasive material. I called it high hardness in one of my videos, and if there's many small strands of glass inside, well, glass is high hardness. It is in the ceramics family, but the material at the macroscopic scale, we would call that abrasive. So let me make that correction. You can use your center punch on materials like this, not on, let's say, polycarbonate. It's likely to split. Lexan is likely to split. So the center punch is useful. And then we are making sure that we have a backing material that's a sacrificial material. It should be rigid, it should be flat, and it should be well clamped. Your speed is likely to be not this full speed, but I'm gonna take this to half because these are not controlling my speed, only the voltage. And you'll hear the speed drop down when I start applying pressure. Oh, well, that was like butter, so barely slowed down. Let's take a look at steel. So this is a stainless steel washer, and I want a small hole in it, and so I'll demonstrate here what it looks and sounds like. And you're gonna hear probably some unpleasant sounds in a second. First thing you probably heard as I pushed on it, the rotation speed dropped down, the pitch dropped down, and also we're not really getting chips or shavings, we're just getting little, well, more like shavings, very fine pieces. We'd like to have a higher torque and push down with a little bit higher pressure so that we get the type of cutting we're after. Okay, so just now you were hearing a pretty unpleasant vibration, and then you were also seeing that we're not plunging very quickly through the material. So that's going to build up heat very, very rapidly. And this is the moment when you want to make sure you have something like carbide. This is a solid carbide bit. In fact, all of the bits designed for fiberglass will be hopefully made of solid carbide. They'll say it on the product pages, and that is to overcome the abrasion without dulling the bits. It's very hard, it's very brittle, and if I drop this on the floor just one time, it's going to crack that bit in half. So the next thing that you can do is lubricate your hole and your bit a little bit while you're working. They make tapping fluid is just equally good for drilling. WD-40 if you don't have those, and like this is a nice little dispenser. It gives you one drop at a time, and in my case I've created my own paste by just thickening it with some beeswax. But anyway, that helps reduce the heat. It helps reduce wherever we have sliding. Instead, we're going to get low friction sliding, so that all the work can be done on the cutting. So I'm still not really enjoying this job here because it's making such extremely fine cuts, and I want to be able to plunge more rapidly. So I'm switching my bit to another one that I know will work out, but it's worthwhile to talk about materials here. So basically all of your traditional tools and tools found at the hardware store is what I mean by traditional. Those are made of something like, well, there are types of tool steel or enhanced beyond that. So the nitride coating or the titanium coating or cobalt steel, got to check if cobalt is the coating or the alloy. But anyway, everything up above here, you can cut that fine without destroying your traditional tools. In this case, I'm going with the cobalt. Costs a little bit more than most of them, and it's very hard, durable. Now you're gonna see and hear a totally different type of operation with the full-size drill involved. Higher torque, higher pressure. I'll stop before I go all the way through. You can notice right away these are beautifully sized chips. That's something that we want. The sound, there was an extremely high-pitched sound, but aside from that, decent vibrations, and no problem that I felt with the bit itself on the material. I'll finish this up for teaching purposes. This hole, you'll see, first of all, it was rotating earlier, too much pressure, and so I reclamped it. And then I've got my hand here holding the drill so that when it penetrates, I don't drive through and slip and hurt somebody. And so we're gonna go here. now we're smoking. Gosh, the video wasn't supposed to go this long. You don't want to see smoke, so I added more oil. And that's a finished hole. Just after drilling and wiping it off, you have a hole that looks like this, and it has a burr on both sides plus a little fragment on the back side. That's going to almost always happen with steel. So this tool will easily, just with the hand pressure, clean that up. And I'm thankful that this is made of a decent tool steel, because I've done plenty of steel trimming with it with no issue. And now you have a gorgeous little chamfer cleaned up edge. It's a little grainy. The visuals, I hope this comes out nice on the full screen. Now I can check my hole size. I'll use the drill bit itself to do my measurement, and I'm just going to check, okay, is it hugging? Does it pass through? With a little wiggling, it passes through. This is almost perfect. Yeah, we were not too sloppy, so it does not have too much extra space. And if I ran this through a couple more times at a very high speed, it would kind of smooth it out. Oh, cool. You guys get to witness me try this for the first time. These pegs that live inside of the, you can see the pins, inside of a bicycle chain, they are press fit. And that's why these tools give you a pushing force to press them in or out. And I just wanted to know, without doing any calculations, can I press fit a 3.6 millimeter pin into a 3.5 millimeter hole? You watched me drill a 1/8 inch hole, which is 3.17 in millimeters, and then I bored it out from there up to 3.5 using a metric bit. So this is what you would call an interference fit or a press fit, where the peg itself is larger than the hole, and this might all jump out and yeah, it's getting misaligned. I'm gonna try one other way. Okay, for everyone wondering, the answer is no. 0.1 millimeters is too much oversize for a press fit, and we were actually shearing part of this hole with the pin. That's a hardened steel pin, and it's a quite soft stainless steel washer, and it was shearing a little bit of that. Hard to see, but just for a quick experiment, there's a result. I don't usually make designs with press fit holes, but if I did, that's not the process that engineers use. We actually have lookup tables for the geometry and the material and how much it needs to stretch and how much interference that you'll have. And this would need to be brought over to a machine shop. So that brings us to machinists. These guys know better than I do on everything I've shared so far. And I strongly recommend, if you're a college student, to bring your project or your question over to meet the machinist around your campus in person and see this this professional face-to-face to bring your question. They're usually extremely helpful, and they're usually able to somehow see multiple steps past the feature that you're working on, and it helps you to plan ahead to improve a design and cut back your work maybe half. Okay, we did not cover everything, but we're gonna wrap up the video here, and here's what I'll do to try to bring order to the chaos. That list that I began at the start of the video, I was filling out the bullet points that describe the sections, like the 1 minute or 2 minute topics, and I will finish up that list. I'll add it as a PDF in, it will be linked in the description. And then that PDF, the last notes that I'll add are that the section of what is not covered. And so that not covered is either going to be the category of what I can drop into the next video, could be a long time, or I'll allow some feedback to give me, okay, we can understand how to do these things from the existing content, or we really want to see more about this. And so it's an opportunity for feedback if you grab that PDF. Thanks everybody, have a great day.